All right, we are recording. Okay, as promised last day, I typed up, no, I just screenshot and copy pasted the example that we were working on last day. So last day, remember we started on trig, but before I get into that, I feel like there was something I was going to say about the test, but I can't remember. It'll come to me maybe. I think it was pretty good. I was expecting it to be better, but that's okay. I know it's kind of a crazy time for you guys, but that's going to be the whole time that you're here, unfortunately. So new career path. All right. So last day we started talking about trig, radians, right? How do radians behave? And we started looking at some problems. It all seems kind of disjointed, but even today we're just going to start to build this kind of vocabulary and just kind of a library of trig things. Okay, so if you have a look at the handout that I gave you, right, there's the important formulas for trig, right? We're going to kind of start to pick through these and make sense of some of them, right? This is just from a different course, but I just stole it because it's nice and compact. So if you want to transfer some of this to your formula sheet, that might be a good idea as things come up. Right. Should I turn this light out too? All the lights out? Okay. So on the handout, the other handout that I gave you, it's got the example from 10.1 that we were working on. And then it's also got some theorems and stuff that we'll be working through today. But still just kind of plugging away at concepts. Okay. Example, let's just call it what they call it, 10.1.3 from handout. This is the one that I was going to make us write out, and then I decided to end class a little bit early, save you guys the trouble. Because we would probably just have written it out and then not done anything. So now we can just get to it. We ended on talking about angular velocity and linear velocity, right? So if we've got a circle, that some object is moving around a circle, then it's going to have some angular velocity, right? Some velocity on the circle. But then we can also straighten that out and talk about a linear velocity, right? And so just as a little recap here, if you've got a circle and some object is moving from this point to this point, right? Then we've got some angular velocity, which we denoted by omega, right? Lowercase omega. And we can straighten that out. I'm probably not going to do a very good job, but we could straighten that out and calculate a linear velocity, v. And we said that last day, what we ended on, let me just steal it from the notes. you guys have it, so. Dun, 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 dun. Copy pasta. Okay. So this is where we ended last day. We said that the velocity of circular motion for an object moving on a circular path of radius r, fine. I'll just put r on here, there. The radius. With constant angular velocity omega, the linear velocity of the object, v, is given by v as r, the radius, times omega, the angular velocity. Okay. So if we know the radius and we know the angular velocity, we can find the linear velocity. So now we get into the example, and I'll steal it from here. Copy. So much copy pasting. Okay. Assuming that the surface of the Earth is a sphere, I don't think anyone here disagrees. But I can't, well. But assuming that Earth is a sphere, any point on the Earth can be thought of as an object traveling on a circle, yeah? Circle, yeah. Because you can slice and dice a sphere into a circle, right? You don't have to think 3D, you can think 2D. So this is the parallel of latitude of the point, right? So we've got latitude, longitude, right? As seen in the figure below, this cute little cartoony looking Earth. Since it takes the Earth approximately 24 hours to rotate, the object takes 24 hours to complete one revolution along the circle. Lakeland Community College, which I can only assume one of the authors works at. It's going to be weird if he ever leaves, but whatever. Is at 41.628 degrees north latitude. And it can be shown, and there's an asterisk that we don't care about, that the radius of the Earth, because we're going to do that later is what they're saying, that the radius of the Earth at this latitude is approximately 2,960 miles, right? And so if we take the circle at Lakeland Community College all around, right, at that exact longitude, latitude, right? Yeah, latitude. We've got a circle, and the radius at that point we can approximate to be 2,960 miles. And then, so we're asked to find the linear velocity in miles per hour of Lakeland Community College as the world turns on this episode. Okay, so we can find the angular velocity, right? Because we know how fast it's revolving around, right, the circumference. It takes 24 hours. And so let's just make some notes here. We want to find the linear velocity, right? And the linear velocity is v is r times omega. I wish if I held my pencil, it would do a nice omega. There. We're given R is 2960 miles. But we need to find omega. But we need to find the angular velocity, omega. So if we think about a circle, right, with a radius of 2960, right, and we know the distance around a circle, any circle, right, in terms of radians is 2 pi. We know the distance around a circle of any radius, because that's the definition of a radian, of any radius, is 2 pi radians. Okay. So it doesn't actually matter what the radius is, but the distance that we have to travel is 2 pi radians. So the angular velocity is still going to be the distance over time. The distance that we're traveling here is 2 pi radians. And the time that it takes us, right, is 24 hours to travel around that circle. We're in the business of canceling here. Then we've got pi radians every 12 hours, right? So what we can say then is that omega, right, the angular velocity is pi over 12, right, radians per hour. Radians is not actually a unit, right? We said that last day was radians. What's nice about them is that it's unitless, and so they're easy to deal with in formulas and things, but we kind of get hung up on it because we want it to have units, right? And so we say radians, but then radians just kind of does nothing to our units. Okay. And so therefore, omega must be pi over 12 hours. This next thing, it's overkill because it's not something that you'd probably think about, but it is something that we should be thinking about, but we probably wouldn't, right? So remember, omega is an angle, right? And so it can be positive or negative. We're just going to make it positive, which means that we're assuming that the Earth is spinning counterclockwise, right? It doesn't really matter which way we're spinning, right? Because we're going a whole rotation anyways. And so we will assume omega is greater than 0, right? Which is assuming Earth moves counterclockwise. So now we can go ahead and say, okay, well, we wanted to find the linear velocity v. V is r times omega. So v is going to be 2960 miles times pi over 12 hours. Which we can just use our calculator, right? You've got pi on there. It's the times to the 10x button, but it's in yellow, so you have to use the shift to get there. So you've got shift pi divided by 12 times 2960. Your calculator is nice because it gives you the exact answer, right? But for now, let's just approximate it. And so get the decimal approximation, 774.9261879 miles per hour, or roughly 775 miles per hour. I'll just inhale.
Yeah.
That's good enough for me. So good. Hey, whatever gets you going. Really? Oh. Have you guys gotten the red rains at Superstore? Anyways, my sister and I used to buy a flat. Anyways, we'd have parties, we'd sell them for $1 each. Anyways, I know. All right, so we've approximated the linear velocity of Lakeland Community College to be 775 miles per hour. Cool. All right. Yeah, just mic drop. That makes sense, right? Ties everything together. No, not really. All right, let's talk about a little bit of terminology here. Just in case it comes up, it's not something that I'm going to test you on, but I'm going to assume that you know. How rude. Ordinary frequency is denoted by a lowercase f, is how often an object makes a complete cycle of motion, right? So once per 24 hours, for example. So how often an object makes a complete cycle of motion. And like I said, the only reason that I'm pointing these out is because it could come up in a problem, right? So this point has an ordinary frequency of 32 hours, right? Then you know that that's how long it takes to make a complete cycle. Since omega is 2 pi f, omega is also a frequency. And it's called the angular frequency of motion. I don't think this is ever going to come up, so. This one will, though. The period of the motion. Period of the motion. Which is denoted by a capital T, which is actually just 1 over F, is the amount of time it takes an object to complete one cycle of motion. To complete one cycle of motion. Right. Okay. So just kind of, especially the period of the motion, right? That's going to be, and if you've done, if you remember from trig before, you probably talked about the period, right? But we'll get there. Any questions about 10.1 before we move to 10.2? No? All right. 10.2 is on the circular functions sine and cosine. Uh-oh, we knew it was happening. But here we are. So we've already used SOHCAHTOA, right, to solve for angles and sides, right? But now we want to expand that because SOHCAHTOA really only applies to acute angles, right? Because we have to have a right angle in there. And so they all have to be less than 90 degrees, right? And so it's not very flexible. So basically we're just going to do the bigger version of SOHCAHTOA, right? And so, because we want to be able to talk about wider angles than just 90 degrees. So we have seen and used SOHCAHTOA to solve for sides, and angles involving right triangles. Right triangles means that it only applies for acute angles. Right? These rules only apply to acute angles, right? Angles less than 90 degrees. Because that right angle is going to be the biggest angle in there. Okay. So we want, and we mean it, we want to expand the idea to apply to any angle. And so definition 10.2 is going to let us do that. So it's on your printout. I'll just bring it over here. And say definition 10.2 lets us do that using the unit circle. Right. The unit circle is a circle with a radius of 1. Right. Unit circle is a circle with radius equal to 1. Special case circle. Okay. So this definition says that if we have an angle theta, so this is going to be any angle, right, on the whole circle, if it's graphed in standard position, remember, is when we start on the positive x-axis and then we move out theta degrees, or theta radians rather, probably. We're going to let P be the point xy, be the point of intersection of the terminal side of P, right? So we're just moving along the arc of the unit circle, and then P is going to be wherever the terminal side intersects. So it's just going to be an indication of where we are on the unit circle. So what this is going to look like, right, is that we'll have some circle, and we've got the origin here. I'll even extend my line a little bit. And then let's say that I've got a line here, and this is my theta. I know that my radius is going to be 1, and that's going to be true all around here, right? It's a unit circle. And then what I'm going to do is I'm going to denote, or pick a different color maybe, here. This point is going to be PXY. So it's the point P at the location XY. And remember that these circles always start at the origin, 0, 0. So we are on the XY coordinates that we're used to. And so that's nice. Where X, right, from this definition, well, the X coordinate of P is called the cosine of theta. So X is going to be cos theta. And Y, similarly, is going to be sine theta. So what that means is that if we're able to find the X and Y coordinate of the point where the terminal side intersects the unit circle, right, that's a lot of terminology in there, right, that might get kind of lost, right? But so the terminal side has to intersect the unit circle at a point P. If we're able to find X and Y, then we'll know that X is cos theta and Y is sine theta. Right, so we're going to use that fact to find cos theta, sine theta.
What's the small a on the, does the y coordinate of P equals sine theta, and it's written as sine theta?
Oh, it's a little, It's because I stole it from the textbook.
Oh.
So it's just a little superscript, and so the etymology of the name sine is quite colorful, and the interested reader is invited to research it. The co in cosine is related to the concept of co-complementary angles. They do a lot of that.
Okay.
It's like, here's some really cool things that's going to take up 4 pages. But anyways, so I mean, I actually meant to look it up because I'm like, quite colorful, huh? Cool. But I haven't looked into it, so I still don't know. Stay tuned. But maybe you're the interested reader that they're talking about. Well, you've been invited to research it. But definitely not something that we're going to get into. I'm guessing it has something to do with sinusoids. Anyways, which came first, chicken or the egg? All right, doesn't matter. So this is the concept, right, that we'll be able to find sine theta, cos theta of any angle as long as we know where that point is on the unit circle. Later today, we'll expand this to be any circle with radius r, right? So it's just going to be a kind of a bigger version, but we're going to start on the unit circle because it's nice and tight. Okay, so if we know x and we know y, then we know cos theta and we know sine theta, right? So that's nice. Let's do a little example. Find the sine and cosine, surprise. Find the sine and cosine of theta equals negative pi. Just kind of starting off with this idea, right? Pi is obviously in radians, right? If you're in degrees, it would have to say degrees, right? So default is going to be radians. We will be able to deal with degrees, right? But default's going to be radians. And so, okay, so find the sine and cosine of theta equal to negative pi. Okay. So if we start by drawing negative pi, the angle, on the unit circle, well, that's not that bad, right? Starting here at the origin, going from here, the standard position, and then we're going to swing around pi, but going clockwise, right? Because it's negative. It wouldn't actually matter if it was positive. We'd get to the same terminal side, right? So they're coterminal, kind of a special case, right? So what it looks like, right? Because one revolution has 2 pi, and so half a revolution must be pi. And so here we've got theta is negative pi. And we did some work sketching these angles last day, right? And I think we landed on, okay, if we've got pi over 6, for example, as one of our radians, we would divide up each half of our circle into sixths. And then just count it out, right? I think that's what we landed on, that we liked. Although I tried to get you down another path, but I don't know, the public has spoken. All right, and I'm great with that. So, no hard feelings at all, no. So here, right, if we know that, okay, so this angle, we have to end up at this side, right? So at this terminal side, well, on this point here, this is going to be P. Well, remember that we've got, here's our X and here's our Y, right? We said that we always start at 0, 0, Right? That is going to be an assumption that we're making, right? We're always starting at the origin, 0, 0. And so if the radius is 1, because we're on the unit circle, right, then the x value must be 1. So P is at 1, oh, sorry, haha, -1, because we moved in the negative direction. Oops. -1, 0, right? Because we've moved 0 distance on the y-axis. Right? We're just on the x-axis. So if we know that point, right, then we know, so x is -1 and y is 0. Therefore, right, cos of -pi must be x, which is -1, right? That was the definition that we said. X is the cos of theta. Theta in this case is -pi, right? So now we know that the cos of -pi must be -1. And same idea, the sine of -pi is y, which is 0. And you can check these on your calculator. If I could figure out, I still haven't looked into how to change the mode because I haven't had to. Do you guys know how to change the mode? I see up top, there's like a little DRG to indicate which mode you're in.
Go to the shift setup and then the angle unit.
Shift setup. Aha. Angle unit. Option 2. Degree radian 2. Nice. Thank you. Too easy. Yeah, I should just outsource all my figure it out stuff. Yeah, so I can just tell you guys what to do. No, I think you'd get fed up with me being like, hey guys, so now I'm in radian mode. So now if I do cos of pi, oh sorry, -pi, I get -1. And if I do sine of -pi, I get 0. Ta-da! So you'll want to make sure that you know how to switch between radian and degree mode, right, on your calculator, even if it's not like this one. And pay attention to it as we flip-flop back and forth. Right. All right. Any questions about that one? Kind of a baby steps. So what we're going to do is to find angles on the circle, right? We're actually going to just use reference angles, and reference angles are essentially, we're just looking at if we've got an angle like here, for example, we can translate that into the same angle in the first quadrant, right? And so we're just kind of translating all these angles to what they would be in the first quadrant. And that means that we only need to know the behavior in the first quadrant, and then we can translate that to different quadrants, right? And so, don't worry, it's all on the handout, but we'll talk about it here. So reference angles are going to be pretty useful because it means that if you flip to the other side of the handout, for example, it means that you don't actually need to memorize this whole circle, right? It only means that you need to know one quadrant really well, right? And so, oh, did you get, oh, you got the handout, yeah? Okay, nice. Right, and so reference angles are going to be useful for that, right? Less memorization. There will be some memorization, but I do not feel bad about it because you get to make your own formula sheets. So, yeah, for the final. So, maybe start jotting down things. Yeah, I think you'll need to kind of rejig your formula sheets, right? But like I was saying earlier, I will give you a practice final, right? And so as you've probably noticed, whatever is on the practice is what you need to focus on for the actual test, right? Same thing goes for the practice final. And we're gonna have, if everything kind of pans out, we're gonna have 2 days of review, right? So in class final exam review. So pretty good. It's a lot of material, but I think you can handle it. Well, you have to. It's a requirement. So when I've made it, I'll let you know. Yeah. But the final is 3 hours, right? And the test has been 2 hours, so it can only be about 1.5 times the length of a test, right? If you think about it that way. And so it can't be that much longer than the test. So there's a lot of stuff that has to get axed from the previous tests.
Yeah.
Did you say the trig stuff?
The big stuff.
Oh, the big stuff.
The big
Yeah.
stuff.
Oh, you want just little tiny obscure things. How about this? All multiple choice. That'd be my dream. But multiple choice is actually really hard to do, right? Exactly, right? Yeah, and there can be questions that you've spent like 10 minutes working on, and they work out to be wrong. Anyways, that's neither here nor there. All right. What did we say? To help us find other angles, we will use reference angles. To help us find other angles, we will use reference angles. And like I said, essentially, if we are very familiar with how angles in the first quadrant behave, if we are very familiar with how angles in the first quadrant behave, we can apply that behavior to other quadrants. We can apply that behavior to other quadrants. So we've got the reference angle theorem, which I'll sneak in there now. Oops. So the reference angle theorem says that suppose alpha is the reference angle for theta, right? then cos of theta is going to be plus minus cos alpha, and sine of theta is going to be plus minus sine alpha, where the choice of plus minus depends on the quadrant that the terminal side of theta lies. Okay. So for example, if we've got a circle and we've got our standard position and we're here at, I don't know, only because I know it from later, negative 5 pi over 4, for example, puts us here. Theta equals negative 5 pi over 4. Right? Negative means 5 pi over 4. Right? If we think about, okay, if we have to move pi to get halfway, then this distance here, right, this would be our reference angle, alpha. I'm actually going to erase this negative 5 pi over 4 on the outside because I put it on the angle instead where it kind of should be. Well, 5 pi over 4, ignoring the negative, right, because that's just the direction. 5 pi over 4, if I take away pi, then the reference angle, alpha, is going to be just pi over 4, right, because then I'll need another pi over 4 to get to 5 pi over 4. So alpha is pi over 4, for example. So now what we can do is we can say, okay, well, thinking about just our XY coordinates here, well, then I can just have, I can replicate alpha equals pi over 4 in the first quadrant. And as long as I know how pi over 4 behaves in the first quadrant, then I can say, okay, well, here, x is positive and y is positive, right? The only thing that's going to change, right, I'm going to be at the same point, except now x is negative and y is positive, right? If I'm down here in the third quadrant, both of those guys are going to be negative, right? X is negative and y is negative. If I'm over here in the fourth quadrant, right, now x is positive, but y is negative, right? And so for these over here, we've got a negative x and a positive y. And then over in this third quadrant, just in general, they're going to have the same values, right? But we're going to have negative, negative. And over in the fourth quadrant, we're going to have positive, negative. And so this is on your handout. And it looks like this. Mm-hmm. So that's what the reference angle theorem is saying, right? If I know what the reference angle is, alpha, then I can say, okay, well, the cos of theta is going to be plus or minus cos of alpha, right? And then same thing, sine of theta, so sine of the original angle, theta, is going to be the reference angle, but plus or minus depending on which quadrant we're in. So here are some go-tos that you should definitely have on your formula sheet. unless you can commit them to memory pretty quickly. Oh. It's got degrees on there, but we're going to focus on the radians. Okay. The most common kind of slicings is over 6, over 4, over 3, over 2. And so we're going to be working with those. And quite often, if we have something else, we can reduce them to something over 6, 4, 3, or 2. Right? And so we can always kind of bring it back to this. And so if we've got our reference angle, right? So here's our reference angle now of pi over 4. Then it says that cos theta has to be root 2 over 2, right? Whether that's positive or negative, right? So cos theta is going to be your x value, right? And sine theta is going to be your y value, right? And then depending on which quadrant you're in, you're going to be able to determine if it should be positive or negative, right? For us, right, we've got a negative x. And so for pi over 4, we've got negative root 2 over 2 for our x value. Right? And then we've got positive root 2 over 2 for our y value. Right? So we can make some notes on here. If we think of this, the theta radians as our reference angle, then cos theta is our x and sine theta is our y.
The radians is the reference angle.
Yeah. So for us, right, for example, just building this into a full-fledged example, find sine and cosine. Oops. Find the sine and cosine of theta equals negative 5 pi over 4. I'm going to say C above, but the reference angle, if you just want to find it mathematically, right, you could say, okay, well, ignoring the negative, right, because that's just the direction, then if I chop off half, right, because I know 5 pi over 4 has gone past the halfway mark, right, and so because 4 pi over 4 would be the halfway mark, right, and so now if I lob off just the half, then I'm left with my reference angle. And so the reference angle is just going to be whatever is between 0 and pi over 2. And so we've got 5 pi over 4 minus 4 pi over 4, right? Just making a note here that this is half the circle is pi, but I'm going to rewrite it as 4 pi over 4, which you can reduce the pi, right? But because I need to have a common denominator, I'm just going to write it as 4 pi over 4. This is going to be 5 pi minus 4 pi over 4. So therefore, the reference angle, let's call it alpha. Alpha is 5 pi minus 4 pi, which is just pi over 4. which is what we kind of deduced on the graph. But now we've got a reference angle. If alpha equals pi over 4 is in the first quadrant, we know from the table, right, and I'll just kind of, I'll steal it here, copy. We know that we want to look at the pi over 4 section. So in Q1, quadrant 1, x equals cos theta, which is cos of pi over 4, which is root 2 over 2. And y is sine theta, which is sine pi over 4, which is also root 2 over 2.
So are we not finding the exact quadrant is in them?
Yeah, so now, so I'm just saying, okay, we can grab these numbers, but those are only for Q1. So now, but because we're in Q2, they're just jumping ahead. But since alpha is in Q2, we need to have negative x, which is negative root 2 over 2, and positive y, which is root 2 over 2. Therefore, if we combine this and say that cos negative 5 pi over 4, right, our original angle, is the same as negative cos of pi over 4, right? Because that's what we just did up above, is we said, okay, well, it's not actually going to be in the first quadrant, it's in the second quadrant, so our cos has to be negative. And so negative cos pi over 4, which is negative root 2 over 2, right? But now we found cos of negative 5 pi over 4 is negative root 2 over 2. And sine of negative 5 pi over 4 is just, again, sine of pi over 4, because we don't have to negate anything, which is just root 2 over 2. Any questions about that one?
So these are all assuming the radius is 1.
Yeah. Yeah. So that's like half an hour away. But yeah, definitely. Cool. All right. So we can combine the reference angle theorem with the table of sine and cosine values to generate this big circle that's on the back of your handout. I guess it's hard to know the front and the back, but. So we can combine the reference angle theorem with the table of sine and cosine values to generate something that looks like this. Notice that these angles are essentially the same, right? Over 6, over 4, over 3, over 2. Those are the exact same that we had in our table, right? And then so here over 2, over 3, over 4, over 5, over 6. Sorry, not over 5. Over 6, over 4, over 3, over 2, and so on and so forth, right? And so it's just different positions in the quadrant, right? But it's hard to see on here, but these values are the same. The only thing that's changing, right, is the sign of the x and the y depending on what quadrant you're in. And so that's why I'm saying, okay, for reference angles, they're so useful because you really only need to know what this one looks like and then how x and y behaves in each of the quadrants. Negative x, positive y, negative x, negative y, positive x, negative y. Right? And so we really only need to narrow it down to the first quadrant, and then we can know what the whole circle looks like. Right? And so you've got this one, but with reference angles, we really only need to know what the first quadrant looks like. And I think this one is on, so this circle is on that trig formula sheet that I gave you as well. And I think it's the same. Just as kind of a side note, I guess, we've talked about coterminal. If I copy this in here, two angles, alpha and beta, are coterminal if and only if cos of alpha is the cos of beta and sine of alpha is the sine of beta, right? And so they have to have the same cos and the same sine, right? And so this feels familiar, right? Because we said, okay, a function is 1-to-1, and I'm not saying that it's the same concept exactly, right? But it's the same idea, right? We said that a function is 1-to-1 if we can show that f of a equals f of b yields a equals b, right? Same type of idea here. Alpha and beta are coterminal if and only if cos of alpha is the same as cos of beta, right? Meaning you end up at the same point for x, and the sine of alpha is the sine of beta, meaning you end up at the same point of y. Right. End up at the same points of x and y, right, where this is x and this is y. I guess I could have given that more room, but Okay. But I think we have a pretty good handle on coterminal, right? Meaning that we just end up at the same terminal side. Let's do an example. Suppose alpha is an acute angle with the cos of alpha equal to 5/13. We're going to find the sine of alpha and use this to plot alpha in standard position. Okay. Little bit of problem solving. Nothing we can't handle. In fact, we've seen all of this before, right? If we just take a step back. And so, okay, we've got a circle. And if it's an acute angle, I'm going to assume it's in the first quadrant just to simplify things. And so I'm going to break up my, here's my y, here's my x-axis. And what we're told is that, okay, from here, right, the standard position up to some point, we're told that this point here is at 5/13 y. Right. And this angle here is alpha. If we want to find the sine of alpha, right, that is finding y, right? To find the sine of alpha, we need to find y, right? Y is the sine of alpha. So once we have y, we know the sine of alpha. We don't need to know what alpha is. Right? What we can do is we can say, okay, well, I'm going to imagine a right angle triangle here. I'm allowed to do that. As long as I drop down perpendicular to the x-axis, right? And I denote that right angle, that 90-degree angle with the little square in the corner. So far, nothing new, I don't think. This distance of x, we know is 5/13. And because we're on the unit circle, this distance must be 1, because the radius is 1. So now, what we actually have is we just have this right angle triangle with alpha here, but a hypotenuse of 1, x of 5/3, and some y that we're trying to solve for. Now we just get to use the Pythagorean theorem. X squared plus y squared equals r squared. we know x squared plus y squared equals r squared. Because if we have r equals 1 and x equal to 5/13, then we can solve for y. You've probably used a squared plus b squared equals c squared, but it's the same, right? C is the hypotenuse, the radius is the hypotenuse, and so we're usually, the equation for circles, right, is going to be using r squared. So now we know, okay, well, x squared is 5/13 all squared, plus y squared is r squared, which is 1 squared. 5/13 squared is 25/169, remembering to square both things inside. We're allowed to bring the square in because we're multiplying or dividing, right? We're not allowed to do it if we're adding or subtracting. Right? Plus y squared is 1. And so we get y squared is 1 minus 25/169. Getting this over a common denominator, right? Multiplying the 1 by 169/169, I get y squared is 169/169 minus 25/169. Y squared is 169 minus 25/169. So y squared is 144/169. If we're solving for y, we need to take the square root of these guys. Square root of 144. We talked about it last day. It's 12, right? 12/13. Or you can just use your calculator. Therefore, the sine of alpha is 12/13. Right. I guess technically it's plus minus, but must be plus in Q1. Any questions about that one?
Why is it 12.69?
Oh, because I'm just getting a common denominator. Because it was actually 1 minus 25/169, but I have to do that. Switcheroo. Okay. All right. Maybe it was even sooner than half an hour. We can generalize these concepts to a circle of any radius using theorem 10.3, which is on your handout. Oops. So now this is going to feel familiar, right? Because we're just going beyond the unit circle to any radius, right? So if Q is a point on the terminal side of an angle theta, same, plotted in standard position, which lies on the circle x squared plus y squared equals r squared, then x is going to be r times cos theta and y is going to be r times sine theta. So the note below, I kept it in there just because it just highlights the fact that, well, so far, right, we were on the unit circle where r is 1, right? And so we had x is cos theta, but that's technically just x is 1 times cos theta and y is 1 times sine theta, right, on the unit circle. But now we're just broadening our horizons to any r. And so we can rearrange this to say, well, then cos theta must be x over r. And if we solve for r in this x squared plus y squared equals r squared, right, then we can solve for r and get the square root of x squared plus y squared. And so depending on what you know in the problem, right, that'll help you pick which version to use, right? Cos theta is either x over r if you know it, or if you don't know r but you know y, right, x and y, then you can use x is x over root x squared plus y squared, and then same thing for sine. I don't know if you guys have been reading the textbook. Mostly probably because I just read it to you. I thin it down a lot, but because they're very wordy. So like, it's weird because it's a very, very formal textbook mathematically. But then it's also kind of colloquial, where it's like, our next theorem makes good use of theorem 10.3. It's just kind of a funny mix. But anyways, that's neither here nor there. It's just something I found. So there's nothing that we really need to say, right? Because we've seen this, now we're just expanding it to any r. And so now we can apply these same concepts. And so we are going to make use of this theorem in this next example. Just wanted to break them up a little bit. So there's kind of 3 different questions inside the question, but that's all right. So suppose that the terminal side of an angle theta, when plotted in standard position, contains the point Q, which is at 4, -2. Find sine theta and cos theta. So for 1, if we've got a circle, and as long as we remember that we're starting here on the x and y axis here at 0, 0, then we're told that, okay, the terminal side, of course, starting at the standard position, the terminal side is at 4, -2. So when x is 4, y is -2. So I'm at a positive x and a negative y, putting me in the 4th quadrant, right? And so what I know is that at some point here, and I don't really know where in the quadrant it is, so I'm just going to map it here, Q is at 4, -2. And I can say, okay, well, that's because here I'm at 4 and here I'm at -2. All right, that's how I found that point. And I can draw my terminal side. So then my theta must be there, right? From standard position, I'm going to 4, -2. Okay. So what we know is that x is 4 and y is -2. From the theorem, right, now we're not on the unit circle anymore, so we have to take into account r. We don't know what r is, but we can solve for it, right? So because then we'll be able to find that cos theta is x over r and sine theta is y over r. And so we need to find r in order to solve cos theta is x over r and sine theta is y over r. Right? I know what x and y are. I just don't know what r is. So this is one of those situations where in the theorem, right, if I know what x and y are, then I can just jump straight to these two equations, right, and skip r. But essentially what I'm doing is I'm solving for r just in the denominator. And because I'm going to use it twice, I'm just going to go ahead and solve for r and then use it in the simpler formula. Right? Simpler in air quotes because it's the same thing. So if we have to find r, right, we've got two right angles to choose from, right? If we've mapped it out like this, right, I could put my right angle here, or I can put my right angle here. Either way, I'm going to be able to use the Pythagorean theorem, right? And so to find r, in general, I know that x squared plus y squared is r squared. X squared is 4 squared plus -2 squared is r squared. Uh, 16 plus 4 is 20 is r squared. So r is the square root of 20. But if you do the square root of 20 on your calculator, it'll simplify it to 2√5. What's nice about your calculator is that it does a lot of this kind of brute work simplification. By theorem 10.3, we know that cos theta is x over r, x being, oops. Turn my equal sign into a circle. That's bad. X being 4. And r being 2√5. So 4 over 2√5. Which, if you plug this into your calculator, right, is going to be, it's going to give you 2√5 over 5. Use calculator. It'll just give it to you. So if you do 4 divided by, and then in brackets 2 times the square root of 5, and it kept complaining because when I put my bracket to close it, it was still inside the square root, so I had to step out the square root and then do it. then it gives me 2 root 5 over 5, right? And so, but if you left it as 4 over 2 root 5, I wouldn't be too upset. Probably not upset at all, actually. Okay. And then same idea, the sine, oops. The sine of theta is y over r, which is y was -2, right? -2 over 2 root 5, which if you use your calculator, you get -5 or negative root 5 over 5. Again, on your calculator. What's really too bad about this type of stuff is I want exact answers, right? So I want the root 5. I don't want to see any decimal approximations for this stuff, right? Because we are talking angles and they'll need to be pretty precise. But your calculator does a lot of that work. So, any questions before we move on to part dos? Okay. I'll just steal it here. Suppose theta is between pi over 2 and pi, with sine theta equal to 8 over 17. Then find cos theta. Okay. So if theta has to be between pi over 2 and pi, right, you need to know where that is in the circle. That's in quadrant 2, right? And so let's start there and say, okay, well, we have to have a circle here. And as before, I'm going to split this up into my x and y coordinates. And at this point, at the positive y-axis at the top here, this angle would be pi over 2. And then on the negative x-axis, then I'm at pi. Right. So what this is saying is that it must be, oops, must be in quadrant 2. Or I'll call it Q2. Okay. We're told that sine of theta is 8 over 17. But here's where we need to hold up and say, okay, well, we're not on the unit circle anymore. And so sine of theta is actually y over r. Right? From theorem 10.3, right? Because we're not on the unit circle anymore. So we can't just say that y is 8 over 17, right? It's going to be y over r. And so what we're going to do, which is 8 over 17, is what we're told. For simplicity's sake, I'm going to let the radius be 17, right? Just kind of eliminate all that work. And so let r be 17 and y be 8. Okay. So far, I know that, okay, my radius is 17. I have to be in Q2 in the second quadrant, and my y value has to be 8, right? So I'm going to be somewhere on this arc here. at some point x, but the y value I know is going to be 8. So if I draw my terminal side here, must be in I'm saying the radius must be 17. And this angle, whatever it is theta. Same idea, right? I can solve for x because I know what the y value must be. So I know that here, this distance must be 8. And so this distance is x. And now I've made this right angle. And so I know that x squared plus 8 squared must equal 17 squared. So x squared plus y squared equals r squared. That's true for any circle. That's the equation of a circle. And so if we know what y is, x squared plus y was 8 squared is 17 squared. 17 squared is, thank you, 289. So x squared plus 8 squared is 64. So x squared is 289 minus 64. So x squared, 289 minus, oops, not divided, minus 64, 225. So x is the plus minus square root of 225. So x is the plus minus 15. But because we're restricted to only the second quadrant, right, I know my x has to be negative. Since x must be in Q2, we know x is negative. So therefore, oops, x must be negative 15. And the question said, find the cos of theta, right? Cos of theta is x over r. X is negative 15 over r, which is 17. So there we found it. Makes me nervous when both you guys were like, wait, what the? What? You both reacted to something. I'm like, I'm pretty confident here, but oh, I know, yeah, it's a long question, but it's because I wanted to find cos of theta. Yeah, I know you guys keep me guessing when you're both like, wait. All right, what's this? This one here. I kept the question references just because we have them on our handout, so it's not actually that bizarre. So in the example that we started with today, right? I'll just say example we started with today. We approximated the radius of the Earth at 41.628 degrees north latitude to be 2,960 miles. Justify this approximation if the spherical radius of the Earth is 3,960 miles. Okay. So what we've got, right, is, okay, so we're on a circle with a radius of 3,960, right? But now I'm at some point that's at 41.628 degrees north, right? So I'm on this circle, and now I want to find, okay, well, what's the radius at that point, right? If I make a slice. So I've made a slice kind of from pole to pole, and then I make a slice the other way. So what we've got looks like this. I feel like I should make it bigger. Same idea, right? I'm going to slice it up into my X and Y's. And I know 41.628 degrees, right, from the standard position is going to be, let's put it somewhere here, 41.628 degrees. You'll want to make sure that you're in degree mode, right? So picking the mode, radian or degree mode, is going to be, it should be fairly obvious, right? Because here we're dealing with degrees, so our calculator has to be dealing in degrees, right? So we'll need to change it back from radians. Because, so what we know is that here, at this point, we've got, is it Lakeland Community College? It's called? Yeah. Okay. And so if we know that the radius of the Earth, right, R is 3960, then what we're trying to find is this distance, right? Because we wanted the radius at that point, right, at Lakeland Community College, which is up north, right? Not as north as we are, but up north. I think I looked it up, and I feel like it's in like around Chicago, that area. Okay. And so we want to find, well, we want to know if the approximation of 2,960 miles for that orange distance, right, is that accurate or not? Okay. So we know that, that X equals R cos theta. Theta in this case is in degrees, right? But we're able to find the cos of theta. So X, X is going to be the radius, which is 3960, times the cos of 41.628 degrees, right? I'll just highlight that this must be in degree mode. So we have to change it before we do anything. And so shift setup, angle input, degree is option number 1, and now I'm in degrees. So now I'm able to find the cos of 41 point, oops, not double point, 628. I'll just show some work here. 3960 times 0.747473547, et cetera, not losing any decimal places, times 3960 is approximately 2959.995241, which if we're rounding 2960 miles. I'm sold. So we could find the radius of the Earth here in Kelowna if we wanted to, if we had to. You might. Probably not, but you might. All right. Any questions? Great. See you guys on Thursday for more trig. Get pumped. Bye, guys.